I am part of MICA, which is the Meta Institute of Computational Astronomy. Some people pronounce it MICA. Some people pronounce it MICA because it's institute. But any of it, it's MICA, and you can see the website there, www.MICA-VW.org. What we are is, at some level, an astronomy department in Second Life. At our core, we have a group of professional astronomers who are trying to figure out the best way to use the metaverse as a way of, enhancing our profession, as it were. So we have professional seminars that are on Friday for professional astronomers to give research talks, and so that we can hear research talks from people that we otherwise wouldn't hear. So that's what we do, but we also have an extended group of interested and enthusiastic amateurs that are associated with MICA as well, and we have a number of popular level events, including this one. And on most Wednesdays, actually not this coming Wednesday, but almost every other Wednesday, we have the Ask an Astronomer event. So go to our website to learn more about MICA. But for today, what I'm going to talk about is how we know that dark matter exists. Now, when I give a talk like this, there's usually somebody in the audience who starts saying, oh, that's not how science works. Such certainty. I can't believe I'm at a science talk. So I want to start with my semantic disclaimer. And so a number of people say, how can you say that you know something? That's not how science works. And, okay, strictly speaking, science never really proves anything. Science can disprove stuff, but it never strictly proves anything. However, I'm going to go ahead and I'm going to make the argument to say that we can say that we know dark matter exists, because the probabilities and the consistent with the data and the number of different lines of reasoning that lead us to believe that dark matter exists means that dark matter, our confidence that dark matter exists is extremely high. There are some things we can say in science. Hold something out from your hand and let go of it. What will happen? It's going to fall. Right? I can predict that. Why? Because we know about gravity. I can even tell you something about the rate it's going to fall. Do I really know that it's going to fall? Well, no. Gravity might turn off because of something we don't understand yet. But the fact is that we basically know it's going to fall. Right? So confidence in dark matter is as great as in evolution? Probably not, because the confidence in evolution is extremely, extremely high. But dark matter is... I'd say that the confidence that dark matter exists is approaching that level, to the point that we're really pretty sure that dark matter exists. And so what I'm going to do today is talk about the evidence that dark matter exists. There are a number of different lines of reasoning. I'm going to talk about all of that and try and convince you that, yes, we really do know that dark matter exists. A lot of people who aren't terribly familiar with it will look at it and say, gee, it looks like you guys have invented another ad hoc thing to try and prop up a failing cosmology theory. And it's not really that at all. Any cosmology theory that we come up with that replaces the one we have right now is going to have to deal with certain observations that, almost independent of our cosmology theory, tell us dark matter is there. But even so, our cosmology theories that we have are extremely well supported and need dark matter to work. It's similar to Newtonian gravity, which we know is not strictly right. As if you were here last week, you heard me say that Newtonian gravity can't predict the orbit of Mercury perfectly right, but we still use it because it's right everywhere else. And the thing that replaced it has to give the same answers as it does everywhere else. So we don't even really say that Newtonian gravity is wrong. We just say it's incomplete. So dark matter really does exist. And here's why we think it exists. Well, first, what is the universe made of? The universe is, at its broadest level, and I've left out several less than 1% contributors like light. That's actually part of the universe. And neutrinos, that's part of the universe. So there's some things that I've left out, but everything that is more than 1% of the universe, it's about somewhere between 2/3 and 3/4 dark energy, about 1/4 dark matter, and about 5% normal matter. And when I say normal matter, I mean that's what we normally think of when we think of matter. It's stuff that's made up of protons and neutrons and electrons. That's what normal matter is. So everything on the periodic table is normal matter. All stars and all the gas between the stars are normal matter because they are made up of protons, neutrons, and electrons. The technical term is baryonic matter. Strictly speaking, baryonic means more than just protons and neutrons and electrons. You can also have pions and J psi particles and all kinds of stuff, but the only ones that are stable are protons, neutrons, and electrons. In fact, even the neutron is not stable unless it's inside an atom. So when we talk about baryonic matter, basically we are talking about protons, neutrons, and electrons. So I've left out all forms of energy except dark energy. All the other kinds of energy are less than 1%. Well, except that mass is a form of energy by E equals mc squared. So if you add up the energy density of the universe, dark energy is 3/4, dark matter, its mass is 1/4, normal matter, its mass is about 5%. Forms of energy that are not mass include like radiation, photons, the cosmic microwave background. That's a form of energy that's not mass. That's less than 1% of the energy density of the universe. So yes, I've left it out, but that's because it's only a small contributor. And how did we get the percent of dark energy? I'm going to defer that question to the end because that's actually part of another talk, really. I will show you a slide later that kind of has that information in it. If you're still unsatisfied about that, please ask that again at the end. So these are the results of a number of different cosmology studies. That tells us what the universe is made of. Now, it's easy to get confused because dark matter and dark energy sound like maybe they're the same thing, especially if I've just said that matter is a form of energy by E equals mc squared. Now, so don't get confused. Dark matter and dark energy are two very different things. And I've listed a whole bunch of properties that sort of define what these things are. So dark matter neither emits nor absorbs light. We can't see it. You can see something that absorbs light because if you put it in front of a light source, it blocks out that light source. Dark matter doesn't do that. Dark matter has been detected by the effects of its gravity. Dark matter is what holds galaxies and galaxy clusters together. It turns out without dark matter, most galaxies and galaxy clusters would fly apart. It transmits, it doesn't interact with light. So you could say that it transmits light because light just goes right through it. Dark matter makes up something like 90% of the mass of our galaxy. Most of the rest of the mass of our galaxy is made up by stars. About 1 to 2% of the mass of our galaxy is in gas and dust. And dark matter has normal gravity, meaning the more mass of dark matter, the more gravity you have. It's attractive, so you fill up galaxies with dark matter, and you're going to have those galaxies will hold themselves together, and they're going to attract towards each other more and more. And we don't know enough to determine whether you convert dark energy to dark matter or back. Probably not, but we don't know what dark energy at all is, so it's impossible really to say that. So dark energy, well, the reason we say dark is the same reason. It neither emits nor absorbs light, so we can't see it. So that's basically the only property shared between dark matter and dark energy, that they both neither emit nor absorb light, so we can't see it. Dark energy was detected not by the effect of, well, it was detected by the effect of its gravity, but whereas dark matter was detected by the effect of its gravity on galaxies and galaxy clusters, then dark energy was detected by its effect on the universe's expansion. So dark matter does not conduct electricity. Plasma is normal matter. Plasma is made up of protons and electrons and atomic nuclei and electrons, really, where the electrons have been stripped off. That's what makes a plasma, and it's all souping around with some photons in there. So that's all normal matter, and we see a lot of plasma. I'll actually show you I'll show you a picture of where some plasma is later. So plasma is all over the place, but it's normal matter, and it's part of that 5%. Couldn't physics just be different in different places of the universe? And ether, yeah. So I'm going to talk about, I'll mention the ether a little bit later. It's not the same as ether theories. Physics different in different places in the universe? It could be, but we've observed to great distances and we can see atomic transitions that work the same as they do here. So at least within the last 10 or 13 billion years, 13.7 being the age of the universe, most of the age of the universe, we have high confidence that physics works the same way here as it does all that time back. And if we come to understand dark energy, we might have a handle on manipulating gravity. Maybe. I mean, we know how to manipulate gravity right now, and that's to move mass around. Would it be nice to manipulate gravity without doing that, so you could have, like, science fiction artificial gravity? Yeah, that'd be awesome. But right now, that's firmly in the category of science fiction. What we know about dark energy is it's probably almost certainly to manipulate, or certainly impossible to manipulate. Now, so again, back to dark energy and its difference from dark matter. Dark energy is driving the expansion of the universe to accelerate. It permeates the entire universe, and it has a negative gravitational effect. So, and this is the key difference right here. between dark matter and dark energy. Dark matter has normal gravity. Dark energy has a negative gravitational effect. So dark energy is making the expansion of the universe speed up. Dark matter, because it has normal gravity, would tend to make the expansion of the universe slow down because all the galaxies are pulled back towards each other. So dark matter is different from dark energy. And that's all I'm really going to say about dark energy today, because this talk is about dark matter. But just realize that dark energy is something different. Now, one other caveat, and I learned this teaching introductory astronomy, is that it's very easy for people to mistake matter that is dark for dark matter. So if you look out in the sky, or you look at pictures of, yes, Sandpiper is exactly right. If you look at pictures of the galaxy, you will see these bits that are dark. Why are they dark? Well, like here, the Horsehead Nebula, famous nebula. What it really is a big cloud of molecular gas mixed with dust, and it's very dirty. It's dirty in that the dust-to-gas ratio is pretty high, so such that if the room you're sitting in, for most rooms, if it had the same ratio of dust to gas, you wouldn't be able to see the opposite side of the room. So it's very dirty. It's very low density because it's interstellar gas, which is always low density. It's higher density than most of it, but it's also many light years wide. It's dust. It absorbs light. It looks dark because we can't see through it, but it's not dark matter because we can still see it. We see it because it's absorbing the light behind it. You see this nice, beautiful pink light behind it, which is actually glowing hydrogen. And then there's the Horsehead Nebula in front of it absorbing it. But what's more, we can see it in the infrared. So this is a really neat picture. There's a lot on it, so I'm going to try and call out a few things to you. Look at this little strip right here. This strip is, if you go and you take an all-sky picture, and then you just cut out the strip that's along the plane of our galaxy, this is what you see. So here's the bulge at the center of our galaxy, and then you can see that there's all these dark lanes in the galaxy. And now, if you get out under a really dark sky, you can see these dark lanes. You have to bring under a dark sky so you can see the Milky Way, but you can really see these dark lanes, gaps in the stars, as it were. That's all this dust that's gummed up along the disk of our galaxy. There's stars there, but all that dust is absorbed. Here, this is in the near-infrared, and what's neat about this is the near-infrared light penetrates the dust better than optical light does. It doesn't completely penetrate it, but it gets through the light better than optical light does, and here you can see a nice classic edge on galaxy. Hey, gee, we really are in a galaxy. There's the bulge. Here are all the stars. They're all there, but here, you've got this dust absorbing it. But if you go out further into the infrared, like say to here, the dust itself is actually starting to glow. Right? So out here in the far infrared, you can start seeing the dust itself glow. So this is not dark matter. Dust is not dark matter. Just that sort of important safety tip there. When we are talking about dark matter, we are not talking about the things that look dark when you look at a picture of the galaxy. Those things that look dark, we can see. They're absorbing other light or they're glowing in the infrared. Now, so we can't see DM at all, correct. We see dark matter indirectly by its effects on other things. So here is the evidence for dark matter. Kinematic, which is just a fancy word for how things move around. Galaxy rotation curves, I'll explain what that means. Galaxy cluster velocity dispersion, I'll explain what that means too. But what you can take this is how galaxies move and how galaxy clusters move. Give us evidence for dark matter. Those two were the first evidence for dark matter. Now we have other evidence. Cosmological structure growth. If we compare our models of cosmology to what we see, we need dark matter to make everything work. Cosmological element ratios. If you put that together with some of the other evidence, you figure out that dark matter can't just be stars that are too dim to be seen, for example. But probably the best piece of evidence, and the most direct piece of evidence, is gravitational lensing that we see in colliding clusters, and I'll get to that at the end. But first I want to talk about rotation curves. So what is a rotation curve? Is a graph of distance versus orbital speed. Although actually I said that backwards. Usually it's plotted orbital speed versus distance. So what do we mean by orbital speed? Well, it's easy to think about the solar system because that's something where we're familiar with orbits in. Here's the Earth. It's whipping around the sun pretty fast. Here's Mars. It's whipping around the sun not as fast. And here's Jupiter. It's whipping around the sun even slower. There's a pretty simple relationship between the speed and the distance from the center of the solar system that an object goes around the center of the solar system, and here it is plotted. So on the horizontal axis we have the distance from the sun in astronomical units, where an astronomical unit is defined as the distance from the Earth to the Sun, or about something like 200 million miles. Something like, 1.5 times 10 to the 11th meters, if I remember correctly. But it doesn't matter. The point is, that's a good distance to measure distances in the solar. Yeah, 8.3 light minutes. And here's the velocity in kilometers per second, which is like kilometers per hour, only 3,600 times faster. So here's the Earth. Earth is going around the sun at about 30 kilometers per second. So hold on to something. Mars slower, Jupiter slower still, and you can see that they fall nicely on this curve. And in fact, what this curve is not just a line connecting the dots. This curve is the theoretical prediction from Kepler's laws, and then the dots are the actual real data, and you can see that, well, okay, we understand the solar system pretty well. Now, the solar system, so these are called Keplerian orbits. Why? Because they obey Kepler's laws. Keplerian orbits is, so that's a jargon for orbits that follow this rotation curve. And when do you get this rotation curve? When all of the mass is right at the center, which is very close to true in our solar system. It's not completely true, because of course the planets have mass, but the mass of the sun is something like 1,000 times the mass of Jupiter. I said that wrong. It's something like 1,000,000 times the mass of Jupiter. No, more like 1,000. I'm sorry. Whatever. It's a few thousand times the mass of Jupiter. I don't remember the exact number, and Jupiter is by far most of the rest of the mass in the solar system. So all except for less than 0.1% of the mass of the solar system is right at the center in the sun. That's right. What's 3 orders of magnitude among friends? Well, if you're in the solar system, it makes a pretty big difference, because it means that we're all orbiting around the sun instead of something else. Now, you may remember from last time, we're not orbiting exactly around the sun, but we're orbiting very close to around the sun, which is why this Keplerian prediction works so well. So when you have all the mass right at the center, you get Keplerian orbits. Now, that doesn't work for galaxies, because you already have seen that galaxies are these big spread out things. So let's think about, how are we going to think about rotation curves? So imagine yourself, that's you, all right, you need to put on a little weight, and you've got a rope in your hand and you're swinging a ball around your head. Woo, 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 right? Fun stuff. We've all done this. And if you haven't, I recommend it, but I recommend you go outside first because you might break something. It's Randall Munro, that's exactly right. This is Randall Munro swinging a ball around his head. And if you do this, you will feel the rope kind of pulling on your hand. As it swings around, the ball tries to pull your hand, and so you pull back on the rope. That's Newton's third law, action-reaction. So it is you pulling on the rope that holds the ball in the circle. If you were to cut the rope, the ball would go flying off in this direction. Whee! But instead, because there's this rope pulling on the ball, it holds it in the circle. So it is the force of the rope holding the ball in this circle. Now, here is a question for you. This is the kind of thing I used to do in my classes. I would put this up, and I would ask them a question. In which case will you need to pull harder on the rope to keep the ball moving in a circle? All right, so you're on the left one, you're spinning slower, kind of slowly winging it around. And on the right side, you're really winging that puppy around. All right? On which one do you actually have to, and don't think about difficulty, right? Because, of course, it's going to try and sag a little bit. Think about you're rolling it fast enough so that it holds up. But then do it faster, in which case are you pulling harder on the ball, on the rope? And this is another thing, do try this at home. Go ahead and tie a rock or something at the end of a rope. And I see that we've got sort of a mix of answers here, so I'll go ahead and tell you the answer is spinning faster. Turns out that spinning faster, you need to pull harder on it. And if you don't believe me, go and try it, right? You will find that the faster you spin it, the harder you're pulling on the rope. If you really don't believe me, go ahead and connect a scale somehow with a spring between your hand and the rope, and you'll see that the force gets higher as you're spinning faster. So this is an experiment you can actually do yourself. Right, and so some people are even, don't do it with a kitty. That's so sad. Some people are throwing up the equations that are related to this and that sort of thing. But the important point here is that a faster orbit means more force is necessary to keep it in orbit. If you don't hold it, right, and a thread will break if spun too fast. Why? Because eventually you are asking the thread to have more tension than it can hold. Yes, and I recommend not actually making yourself throw up, unless you like that kind of thing, but that'd be strange. So the important thing here is that the faster the orbit is, the more forces that is needed to keep it in orbit. So let's look at galaxies. Well, all right, first of all, we want to measure the rotation curve, which means we want to plot the velocity that stuff is moving as a function of how far it is from the center of the galaxy. All right, well, how do we measure it? Well, we measure it using the good old-fashioned Doppler shift, which is a nice thing. You may have heard this with sound. If a car goes past you, you'll hear the car make a sound something like this. And what's happening is, as the car is coming towards you, you hear a higher pitch, and when it passes you and is going away, you hear the lower pitch. Well, pitch in sound waves is related to the wavelength of the waves. A higher pitch is a shorter wave. A lower pitch is a longer wave. The same exact thing happens with light. So if you're looking at something and it would have given you light of a certain wavelength, if it's coming towards you, so this is me here, I need a haircut, looking at a star, here, and I need to get something done about that nose too. Here I am looking at a star. If that star is coming towards me, the light I see from it will be blue shifted. It'll be shifted to shorter wavelengths, and shorter wavelength light is bluer. And if the star is moving away from me, the light I see from it will be red shifted. Red shifted light is light with a longer wavelength. Right? And the Doppler shift works like that. So we could do this for stars. We go out and we look at stars in a galaxy. If we measure, say, an atomic transition line for hydrogen, for example, there's a line at 6,563 angstroms. If you're an astronomer, that's 656 nanometers if you're a physicist. Same thing. It's a well-known line of hydrogen, and if you see that line and you see it at a slightly different wavelength, you'll say, aha, it's the Doppler shift. It's because the stars are either moving towards me or away from me. So that's exactly what we do. We go out and we look at these galaxies. I could have sworn I clicked next. I'll click it harder. Uh-oh. My slide projector has stopped listening to me. Oh, there we go. Now it's probably going to jump forward multiple times. Yes. Because I hit it a few times. So let me hang on while I try and get control of my slide projector again. All right. So what we do is, right here, as you look at, yeah, it has been built. This is a galaxy that's tilted, so we're kind of looking down on the top of it. So if it's going around this way, right here, the stars are moving partially away from us. And because they're moving away from us, we'll see a red shift. And over here, they're moving towards us. Because they're moving towards us, we'll see a blue shift. If any of you guys are wearing like a Mista tool or something like that, could you disable it or take it off? Because I think we're starting to get some script lag in here due to the number of people we've got. That's why I was having trouble turning pages. So that's what we do. Now, so that's how we measure the rotation curves from the Doppler shift. So the next thing we want to do is figure out what rotation curve do we expect. If all the mass was right at the center, it would be a Keplerian rotation curve. But we don't expect that because, look, there's stars out here too. And so the way to think about it is for a star at a given distance, so there's a star right here at the center of this circle. What is holding it moving in the circle? It's moving off in some direction. It would go flying off in this direction, except there's stuff holding it in a circular orbit. And because it's in a circular orbit, there must be just the right amount of mass to hold it there. Well, it's all the stuff between here and here is what's holding it into the orbit. It turns out that the stuff out here doesn't really matter. You'd think it would be pulling it away, but by the same token, if you look at the stuff out here that is farther away than the stuff between here, the center, and where its orbit is over here, the stuff out here pulling towards it ends up compensating for the stuff over here. It's not perfect. It turns out it is perfect in a spherically symmetric situation. It's not perfect in a disk galaxy, but it's very close. So for purposes of kind of understanding what's going on, you can think that all the stuff that is closer to the center of the galaxy than the star that's going around, so all the stuff between here and here, and also on the other side, all that stuff, all the stuff within the circle the star is making, that amount of stuff is what is holding the orbit in. So if the orbit is faster at a given distance than you expect, that means there's got to be more matter than you expect. So already you should expect that things that are farther out from the center of the galaxy should be moving faster than is the Keplerian case. Why? Because there's all this extra mass here. In the solar system, all the mass is right here, and this guy would be moving relatively slow. But in the case of something that's distributed like a galaxy, there's more mass. You can see it. Look at it. Look at all those stars. They all have mass. So this thing is going to be moving faster because there's more mass holding it in, and if it's going in a circle, it's going to be a faster circle because there's more mass and there's therefore more gravity. So by looking at all these stars and figuring out how many stars there are and how big they are and looking at all the gas, we can add up the gravitational effect we expect and figure out how fast everything ought to be moving. And that's what I have on the next page. All right. So first of all, here's the Keplerian curve just for comparison. It looked like that before. If we observe the matter in the galaxies, the stars, you actually expect a curve that looks something like the orange curve. And it is. It's going faster than the Keplerian curve because as you go farther out, there's more stuff there. All right, so this is what we expect from all the stars and gas we can see. What we really observe in terms of speeds, though, is this. So there's a gap. If we add up all the stars and gas that we see, there isn't enough gravity to hold the galaxy together. All right. Stars and gas in the outer part of the galaxy are moving too fast. Notice towards the center of the galaxy, if we add up all the stars and gas, we get it either exactly right or pretty close. But as you get further and further out, the discrepancy gets bigger and bigger. So what that's telling us is, it's telling us one of a couple things. Either it's telling us that we don't understand gravity right, and we're getting gravity wrong out here. You know, that was a real possibility that I think we've more or less ruled out now. But okay, that's one possibility. We don't understand gravity right. Second, that was one possibility. The other possibility is that there is more mass in the outer parts of galaxies than what we've accounted for. Stuff we can't see. That we call dark matter. Now, if you remember my talk a couple weeks ago, we saw some of the motions of Uranus's orbit could not be explained by all the stuff we could see, and people used that to predict where Neptune would be. So in this case, we have all this difference, and so we can predict where all this extra mass ought to be. And that's what we call dark matter. It's the stuff that's holding the galaxy together. All these stars moving this fast would go winging off into intergalactic space, except there's enough gravity to hold it together. All right, so when we observe galaxies that have collided, are the orbits red, blue, shift, Keplerian? No. When we looked at collided galaxies, it's a big, huge mess. You have stuff going all over the place. The nice, clean, circular orbits get all screwed up as stuff interacts with each other and gets all stirred up. So you tend to see a nice, huge old mess as galaxies collide with each other. And it's pretty cool, actually. So right now I'm talking about spiral galaxies where it's more simple to interpret it. I'll talk about mess in a little bit. All right, so that is, right there, was one of the first pieces of evidence. All right, so why do objects close to the center of the galaxy move much slower? And the reason is because there's actually not that much stuff, relatively speaking, at the center of the galaxy. Now, it's a little perverse because the center of the galaxy is denser than everywhere else, but it's not like the solar system where all the mass is right at the center. And yes, there is a supermassive black hole right at the center of the galaxy. So the orbits, actually, if you look at the very center, within a few hundred light years of the center, and by the way, the kind of scale we're talking about from here to here is like 30,000 light years. So you're not going to see a few hundred on this plot. If you look at a few hundred, there's going to be a huge spike. Things are moving really quickly because of all the mass right at the center. But once you get outside the inner few hundred or the inner 1,000 light years, there's just not all that much stuff there. Stuff in the galaxy tends to be more spread out. Galaxies are much more spread out than solar systems. And so since there's not so much mass, if things are going in a fast circle, they're going to move out and not stay that close to the center of the galaxy. Yes, and Rudy's right. It's actually a very mesmerizing screensaver, the galaxy collisions. They don't do it right because they don't have kinematic friction, so they tend to spread the galaxies out into individual stars all over the place. All right, so it's actually not true that the laws pertaining to time are consistent, and when you move at the speed of light, the rules are different. It's actually true that it's not true there's a smooth transition. So as you get close to the speed of light, the laws start changing and changing, and as you get really close to the speed of light, they change more, but there's a smooth transition. As long as you're less than like a quarter the speed of light, you can forget about relativistic effects, depending on how precise you need to be. So yes, and is it possible that gravity works on a different scale? Yes, and I will address that later. How could it be we got the mass prediction wrong, i.e. more from black holes and brown stars than we predict? That is ruled out now, but it wasn't ruled out originally, and that's a good idea. That's a good thought, and that was certainly a possibility, and I will talk about that a little bit later too. What would I expect if galaxies were uniformly distributed through all space? In that case, the gravity of dark matter would cancel out on galaxy scales. It wouldn't affect the rotation curves of galaxies at all. It would affect the expansion of the universe, but if it was uniformly distributed through all space, it would not affect the motion of galaxies at all, because there's the same amount of dark matter in one direction as another, and that would offset. So it would only be seen on the expansion of the universe. Right? Here's another thing. We've looked at our galaxy. We've looked at other galaxies. In fact, here's a plot of a whole bunch of galaxies, and you can see that they all kind of follow this curve of a rising curve and then kind of flattening out. It's not all perfect, but they're not all perfect, but they all have the same basic shape of rising and then flattening out. So you look at spiral galaxies, and they all do kind of the same thing. Could dark matter be black holes and dark energy be Hawking? Dark energy is not Hawking radiation. Dark matter be black holes. I'll talk about that later. The sun is not at the center of our galaxy. In fact, let me go back a couple of slides here. I'll show you where our sun is. Previous. Our sun's about here, actually. Our sun is the circled star. So if you look at the disk of our galaxy, our sun is something like halfway out. So our sun is not at the center of our galaxy, but it's off-centered. So yes, dark matter occurs in the outer regions of galaxies, but actually it occurs all the way through galaxies. It's that it's spread out farther than the stars. So that's why halos are mostly dark matter. Towards the center, it's a better mix. Now here's another thing. I talked about velocity dispersion. What happens when you have a messed up? And this is when you look at an elliptical galaxy or galaxy that's a big mess of colliding galaxies, which actually is sort of what an elliptical galaxy is, or if you look at clusters of galaxies. So in a cluster of galaxies, you have both elliptical galaxies, which I've represented with little red blobs, and spiral galaxies, which I've represented with these little spirally thingies, and they're all flying around every which way. Some galaxies are going slower than others, some are faster, and it's a big, huge mess. However, you can look at sort of the average speeds or the distribution of speeds. And so if you first of all, the average speed is going to be 0, about the center of the cluster. But the velocity dispersion is what we call sort of the average offset from 0 if you take just the speed of the galaxies, right? So the velocity is 0. Because some things are going one direction and some things are going another direction, and velocity is speed plus direction. But the average speed is not 0. So if we take the average speed, that's something like what we call the velocity dispersion, and it's dispersion because its velocity is going every which way. If you look at the velocity dispersion in a galaxy cluster, and you compare that to the mass of all the galaxies you expect from looking at the amount of stars that you can see in the galaxy, the velocity dispersion is much too high. And this was noticed back in 1933. Fritz Zwicky, a well-known astronomer who was also an astronomer who had some trouble getting along with other astronomers. Nobody wanted to believe him because he was a strong personality. So people didn't really want to believe him because he was annoying, but he was right. He's had this inspiration early on. Look at these clusters of galaxies. Look how fast they're moving. They all ought to be flying off into intergalactic space, and yet we see lots of galaxies, clusters of galaxies out there. So something's got to be holding them together. 10 to 100 times the mass is missing. All right? Zwicky noticed that. Later on, when Sandy Faber started talking about spiral galaxy curves, Sandy Faber was one who I think was a little more politic than Zwicky, and so people believed her. But of course, now we look back and we realize everybody was right. That most of the mass in galaxies and galaxy clusters we're not seeing. When we add up all the stars and gas that we can see, we're not accounting for most of that mass. Here's another line of reasoning. All right, so the kinematics were the first line of reasoning. This and the spiral galaxy are the first line of reasoning. In many ways, they give us the best precise measurements of the amount of galaxies. And these are all Doppler derived as well. So basically what you do is you look at the overall average Doppler shift of each galaxy in the cluster, and then you can figure out how fast the galaxy as a whole is going. Right? So kinematics are strong evidence for dark matter all by themselves. There is other evidence. Cosmology, for example, which I think I clicked next, so I hope it shows up. Next. There we go. Okay, there's a whole lot of information on this slide. What is plotted, first of all, we use these special letters because, I don't know, we like to have our own special language to make everyone else look confusing. Omega M is mass density, and when we say mass, we mean regular matter plus dark matter. So that's what's plotted along this horizontal axis, and they're plotted in units that are normalized, and don't worry about what they are. They're just some freaky unit where the omega M is probably between 0 and 1. So that's the mass density of the universe compared to something we call the critical density. And then omega lambda is the dark energy density. So that's what's plotted along this. And then we've got 3 different experiments that are plotted. So first, BAO, baryon acoustic oscillations. Well, that's very technical, but basically it's telling you about clustering of galaxies. If you look how well galaxies cluster to each other, it says that somewhere, I'm going to make my laser red so you can see this, somewhere in these green lines is where we expect these 2 parameters to fall. So you see it's not very sensitive to the dark energy density, because the dark energy density could be anywhere along here. But it's very sensitive to the mass density. It tells us the mass density has got to be somewhere between like 0.25 and 0.5. All right. That's what BAO tells you. That's what clustering of galaxies. CMB is observations of the cosmic microwave background. Cosmic microwave background is sensitive to the sum, mostly. And the cosmic microwave background tells us that the sum of omega lambda and omega m has to be close to 1. All right. And then finally, we have supernova observations, and the supernova observations are the best sort of direct evidence that the expansion of the universe is accelerating, the best direct evidence for a cosmological constant, and they're most sensitive to something like, and I did it wrong, this should have been omega m minus omega lambda. That little thing right there is supposed to be a minus. So the supernova tells us the parameters have to be somewhere in here. And you notice all 3 of these collide in this one spot. And this one spot is around omega m of 0.3 and omega lambda of 0.7, something like that. Okay? Well, here's the neat thing. If I take out all the galaxy clustering, which means I can throw out all the stuff about kinematics I told you before, and we're looking at 2 completely different things. Look at the cosmic microwave background, which I talked about a month ago. And look at the supernova results. And you put the 2 together, the 2 together tell you, well, they only overlap here. And the 2 together give us the same thing that the galaxy clustering results give us by itself, that omega m has to be about 0.3. All right. So, and again, I'm not going to talk a lot about the expansion going faster and faster. It's probably not going to stop. It's probably not going to go backwards, but that's a whole other talk. So I'm going to defer that either to the end or to the next Wednesday Ask an Astronomer. The point here, though, is that if you look at just the stuff I talked to you about before, but if you look at these other cosmological observations, it tells you to explain our cosmological observations, we need this much mass in the universe. The total mass in stars and gas we see is somewhere around 0.0 a few. I don't remember if it's 0.01 or 0.03 or 0.04, but it's 0.0 a little bit. That's all the mass in stars and gas. We need to have something like 0.3. So there's a factor of 10 missing in mass. So there's got to be dark matter. There's more mass than we can see. Here's another cosmology argument, structure formation. Start from the cosmic microwave background. That's the mass distribution a few 100,000 years after the Big Bang. Do calculations of how structure grows. So where there is, let me move it away. I'm getting all excited and talking loud. So where there's higher density, stuff is going to kind of collapse, and you're going to make clusters of galaxies. And where there's lower density, well, stuff's going to collapse away from that. You're going to make voids. And if you do those calculations, you can get a distribution that looks something like this. So this is from a calculation. Over here is real data. This is from the Sloan Digital Sky Survey. All right. So notice what you see. Well, you see these clumps, sort of like there, and you see these voids between them. And here's a simulation of that data that shows you basically the same thing. But now no, you won't see exactly the same pattern, because this is a simulation that doesn't have exactly the same, it doesn't show all the galaxies in exactly the same place. But the basic way it looks is the same as here. Right. To get this simulation right, you have to put in dark matter. You have to put in more matter than we can account for just looking at all the stars and galaxies. So for the cosmology to work, we need to have this dark matter. Right? So 2 lines of evidence I've given you now. One is the kinematics that says there is more matter holding together galaxies and holding together clusters of galaxies than we can see. The second is cosmology. In order to explain the observations we see of the universe as a whole, be it the expansion of the universe and the cosmic microwave background put together, or being it large-scale structure, clusters of galaxies and superclusters and the voids and the filaments. In order to explain all that, we need dark matter. We need to have 30% of the energy density of the universe in dark matter, and yet the amount of mass that we see only corresponds to about a few percent. So what does all this mean? There's more mass in galaxy and in clusters of galaxies than we can account for from the stuff we can see. Dark matter, the stuff we can't see. But what is it? What is dark matter? And this is where somebody asked a good question earlier. Dark matter candidates, one-time dark matter candidates, and I say one time because we've kind of ruled out the first one. So we start with MACHOs, massive compact halo objects. It's a, if you're going to have to name everything after an acronym, you might as well come up with some fun acronyms sometimes. So MACHOs. MACHOs, what are they? Massive compact halo objects means things out in the halo of our galaxy. Possibilities include very dim, undetected stars. It was possible that red and white dwarf stars both are small enough and dim enough that we can't see them very easily very far away, and maybe we just haven't accounted for all the red and white dwarf stars there are. Very real possibility, okay? It may be that there were just lots of red and white dwarf stars out in the halo that we had not detected yet, and that's all the dark matter was. It was not dark matter, it was just insufficiently bright matter as such, right? They could be what failed stars, which is applying all kinds of value judgments to brown dwarfs. A brown dwarf is a star that is not massive enough to support fusion at its core. In that sense, it's a failed star because it never really became a star, right? So, yeah, and so bowers, could you tell if it's diffuse or dense? Yes, they could, and in a sense, if you have lots of stars spread out, that effectively is diffuse mass. But if they're compact halo objects, there will be specific things. I'll mention that in just a second. All right, gas we haven't detected, or black holes. Actually, gas we haven't detected would not be MACHOs, so I shouldn't have listed that here, or black holes. Okay, so these other things are all MACHO candidates. Well, people have done searches for MACHOs, and what they do is they look at a very dense star field, and as a MACHO moves in front of a background star, it will briefly gravitationally lens it. So there have been MACHO searches that do exactly this. And they found some, right, that you find dim stars out there, or maybe brown dwarfs, but they have not found nearly enough to account for all the dark matter. So there's not enough MACHOs to be dark matter. The other leading dark matter candidate is, of course, WIMPs. If you have MACHOs, you have to have WIMPs. WIMPs for weakly interacting massive particles. These are all diffuse. WIMPs are defined by they do not interact electromagnetically, including with light, which is electromagnetic. They do interact via gravity. They may interact via the weak force. So the weak force is one of the four forces of nature. It is the force that's responsible for a lot of radioactive decay. It's not the thing that holds atomic nuclei together. It's much weaker than that, and that's why it's called the weak force. Neutrinos are an example of something that fits all three of these. Neutrinos do interact via gravity. We know that neutrinos have some very small mass nowadays. They do not interact electromagnetically, but they do interact via the weak force. So WIMPs are something similar to neutrinos, but they're not normal matter. They're not made of protons and neutrons and electrons because protons, neutrons, and electrons interact electromagnetically. So WIMP, and so massive sounds big. When we say massive particles, what we mean is not massless. That's correct. But what's more, almost certainly they're more massive than all the particles that we've made in particle accelerators today. The reason being, how massive a particle is tells you how much energy that particle has. If it were low enough mass, we probably would have made them. And yes, neutrons do interact electromagnetically, it turns out. They don't have a charge, so they don't interact with electromagnetic or electrostatic force, but there's a magnetic moment on neutrons. So they will interact with magnetic fields. So neutrons do interact electromagnetically. Free Higgs particles, who knows? I don't know enough about Higgs particles to say much about them. There's lots of theories that would say they may interact via the weak force, actually. So there's a lot of good reasons to expect that WIMPs, in fact, their name suggests that they interact weakly. All right. So probably they do interact via the weak force. A lot of the dark matter candidates we have would interact via the weak force. So there's good reasons to suspect that, in fact, they would interact via the weak force. Right. So as I said, today we know MACHOs can't be most of the dark matter. We need exotic particles of some sort. Well, how do we know this? Well, partly because we've ruled out MACHOs because we looked for them. Well, what about gas we have? Can it just be very thin, tenuous gas? And the answer to that is no. And how do we know that? Well, I'm going to have to talk about the history of the whole universe. The universe starts with a bang, right here. We don't understand that at all, but we understand most of the stuff from here on out pretty well. Lots of things happen. There's dark ages, stars form, the sun forms, and finally there's you, right here. I want to ignore most of this. What I want to focus on is about 10 to 20 minutes after the Big Bang when the elements form. So the universe is a big soup of protons and neutrons and electrons and photons at this stage. Okay, it's a big soup of all that, all interacting with each other, and the elements form, and we understand that nuclear physics very well, that we can predict the ratios of the different elements. So what this plot on the horizontal axis is the ratios of various different elements to hydrogen. So helium, helium-3, lithium, deuterium, that's what these 4 lines are. What is their relative abundance compared to hydrogen, which is most of the universe, all right, as a function of the baryonic density, all right? Baryonic, meaning the density of protons and neutrons. This green line tells you how many baryons we would need to get the mass to hold all the galaxy clusters together. This here, this gray thing, tells you the observed densities of these various elements all fall here. So helium is observed to have this density. Deuterium is observed to have that density. Helium-3 is observed to have that density. Lithium is observed to have that density. So that tells us, or that fraction, I'm sorry, I was saying densities, what I really meant was fractions. So the fractions of the elements all line up for this density, which tells us if we really believe we understand nuclear physics, which we do believe because we have used it to blow a lot of stuff up, as well as to do other kinds of nuclear physics experiments that are less destructive in cyclotrons and things. We understand nuclear physics well enough that the density of the early universe in baryons has to be a lot lower than the total mass we need to hold everything together. So where does this leave us? Galaxies are rotating too fast to be held together by the massive stars and gas that we see. Galaxies and clusters are flying too fast for the cluster to be held together by the massive stars and gas that we see. Measurements of the ratios of light elements tells us that there are not enough protons and neutrons in the universe to make up the extra mass. So even if it was just stars or gas or something that we haven't seen, that can't be the dark matter, because protons and neutrons can't make up enough mass. So therefore, there must be some unseen, dark is unseen, matter, which is made of something other than normal protons and neutrons, also other than noble protons and neutrons. Noble protons and neutrons are protons and neutrons that are in neon or one of those. Normal protons and neutrons. Actually, protons, that's kind of a stupid thing to say because protons and neutrons are normal. So it's other than normal matter. Okay? Well, all right. Now, here's somebody who was asking this question earlier. Is it possible we don't understand gravity right? Well, yes, that's entirely possible. Somebody was asking almost specifically the question, could it just be that in the far parts of galaxies, gravity works differently from how we thought it did? So, can we get by without dark matter? And this was Milgram proposed in 1983, a specific model, which here it is. A modification of the Newtonian dynamics is a possible alternative to the hidden mass hypothesis. And the basic idea is, well, okay, Newtonian gravity is well tested in the lab. It's extremely well tested in the solar system. But galaxies are big extrapolations in scale from these regimes, in that the gravitational force on stars very distant from the center of the galaxy turns out to be really low. And they take forever to go around. Right, and so is it right, and what Bao says really hits the nail on the head. He's not sure that, or she, sorry, is not sure that it's more parsimonious than the dark matter, but it feels like it is. A lot of people felt that way. A lot of people feel like dark matter is more parsimonious than modifying gravity we understood. So it's almost sort of a philosophical or an aesthetic argument, which is more parsimonious. But, well, we got to think about it, all right? And here's the basic idea. Maybe galaxy is just different on the scale of galaxies, and we can explain galaxy rotation curves without needing to invoke dark matter. Here's another choice quote on this. This is a review from 2002 by Sanders and McGaugh about MOND, or modified Newtonian dynamics, which is basically Milgram's idea. And I'm going to just go ahead and read this quote. It may be argued that MOND is a speculative topic for a review in this series. Right? ARAA is a very serious astronomy journal, so, how could we talk about MOND? In our opinion, the subject of dark matter, and Virginia Trimble is cited here, is, in the absence of its direct detection, no less speculative, particularly concerning that the standard model of particle physics does not predict the existence of candidate dark matter particles with the necessary properties. And this review and other reviews that have been done went on to conclude that, well, given the evidence we had on galaxy rotation curves, it was really hard to distinguish between dark matter and saying we just didn't understand gravity. What we really needed in order to prove that dark matter is there is sort of direct detection, which means seeing matter where we don't see baryonic matter. Well, okay, we've done that. But to understand what we've done that, I have to take a slight sideline and talk about galaxy clusters, which I've already been talking about. But here's your list of facts about galaxy clusters. So when you're playing Trivial Pursuit and somebody says, what percent of the mass of a galaxy cluster, of the baryonic mass of a galaxy cluster is stellar, you can answer, right, and get a little wedge in your little thing. So galaxy clusters are hundreds to thousands of galaxies, all clustered together in something that's something like 3 to 30 million light years in diameter, which is small on the scale of the universe, is big on the scale of a bread box. 10 to 15% of the baryonic mass, meaning the protons and neutrons, is in stars. Most of the baryonic mass, it turns out, is in very hot million-degree gas that's spread throughout the cluster. Right? This is part of Zwicky's dark matter, in fact. Zwicky said, hey, I need more mass than I can see in these galaxies. Well, here's some of it. Turns out it's not enough, but some of it is the X-ray emitting intracluster plasma. We call it X-ray emitting because that's how we see it, right? What really is important is that it's plasma and it's at millions of degrees, all right? And because of that, and why doesn't, yeah, that's an excellent question. It will, but the time it's going to take to cool down is longer than the age of the universe. So it's radiating some of that energy. The X-rays we see is that energy radiating. The reason it doesn't radiate faster is because it's so low density. So one of the dominant ways for the energy to radiate is for an electron to pass a proton or another electron and curve and radiate a little bit of its energy and slow down. For example, that's called free radiation in astronomy jargon, and that's happening. But because the density is low enough, it doesn't happen often enough for the energy to efficiently radiate away all that fast. So it's going to take billions of years. It's not, and George says it's not quite blackbody radiation. It has a different spectrum from blackbody radiation. It's not pure thermal. We do talk about thermal free radiation, but it's not quite the same thing. All right, so it's plasma radiation, and we see it in X-rays because that's where a lot of it is. So the baryonic mass is an X-ray. That's where most of the protons and neutrons, it turns out, right? These galaxies are kind of along for the ride, right? But again, if we use standard Newtonian gravity, not Mond, the gas accounts for something like 5 to 15% of the total mass of the cluster. In other words, most of it still has to be dark matter. Well, okay, let's talk about merging galaxy clusters. Galaxies are mostly collisionless. That is, they pass past each other. Some galaxies do run into each other, but by and large, if you take two galaxy clusters and run them into each other, it's like taking two handfuls of sand and throwing them past each other. Occasionally, 2 grains of sand will run into each other. Mostly the sand just goes past each other. The intracluster gas, however, is a big blob, and it does interact via fluid stuff, fluid dynamics, viscosity. Well, actually, it's plasma fluid dynamics. So there's all kinds of stuff that goes on. But that's like taking 2 handfuls of water and trying to splash it into each other. If you take 2 cupfuls of water and you manage to throw it at each other, it splashes in the middle and kind of all stops there and splashes around and makes a big mess. So the galaxy clusters are collisionless, throwing 2 handfuls of sand at each other. Mostly they pass past each other. The intracluster stuff is more fluidy, and it's like throwing 2 blobs of water at each other. If there is non-baryonic weakly interacting dark matter, it will also be collisionless. Because it's weakly interacting, mostly particles don't run into each other. Yeah, dark matter exhibits momentum because it has mass, and anytime you have mass and you move it, it has momentum. So it'll have kinetic energy as well as mass energy. Right, so non-baryonic, weakly interacting dark matter will also be collisionless. Well, all right, but how can we figure out where there is mass that we can't see? Well, from its gravity, but what we want is to have another way to do it. Well, it turns out it's still from the gravity, and that is, there's this thing called gravitational lensing. If you look at a star, here's a distant star, and there's a star in between you and it, it turns out that the gravity of this star will bend the light rays coming from this star. Right, so in this case, this is strong lensing that we're talking about here. In this case, the light ray that was going in this direction gets bent by the gravity of this star and comes at you in this direction. So that what you see is light coming from this direction, which makes you think you'd actually see a star out here. Similarly for down here. So this is a case here. This is Einstein's cross. The thing in the middle is the lensing object, this. And the 4 stars on the outside, this is actually quasars, but the principle is the same. These are quasars that you see multiple images of as a result of the bending of light here. They're all the same quasar. but you see multiple images because the light rays were bent here. So gravity can bend light. Here's a classic example, the cluster Abell 2218. And because of the expansion of the universe, the image has now started to cover the letters. But there are two galaxy clusters here, actually. All the yellow things are foreground galaxies, and then these streaks you see are background galaxies from a background cluster whose light has been streaked and distorted by the galaxy of the Fuss. And yes, Reynolds numbers are used when calculating. I mean, there's all kind. I'm not an expert on plasma fluid dynamics, so I can't really tell you. I mean, Reynolds numbers probably go into it, but I don't know the details. What is there a star in those other two places, the light from both? How can you distinguish the two? Well, all right, so there's ways we can distinguish. But if you measure the redshifts here, you'll see that there's two different redshifts. So the yellow galaxies are all at one redshift. I don't remember what it is. The other streaks are all at a much higher redshift. And in fact, there's other galaxies mixed in as well, but mostly that's what you're seeing here. So that's one way to distinguish is by the redshift. And we see all the high redshift ones are stretched out. So what this tells us is that we can see where the mass is by looking how galaxies get stretched out and distorted. Now what we really do is this thing called weak lensing, which is where it's not big, huge effects like I showed you before, but if I am looking at a galaxy here, and it's going between there's all the mass in the universe between it and me, the galaxy's rays are going to be a little bit distorted, only at the few percent level. So if we look at a whole bunch of galaxies, background galaxies, in a field of view, we can see them all distorted at a few percent level, and we can figure out how much mass the light has gone by in order to distort them all. This is very hard to do. In order to measure the distortions at the few percent level is a very difficult problem. But, scientists do difficult things, and eventually they figure out how to do it. And so now we have this thing called the bullet cluster. Now, all right, this is another complicated image. So what I'm going to do is, first of all, point out, you notice here there's a collection of galaxies, and there's a collection of galaxies. What they are two clusters of galaxies that have actually passed through each other. How do we know they've passed through each other? Well, the pink is X-ray observations of the intracluster gas, this hot X-ray emitting gas, and you'll notice that it's all kind of clumped in between the two clusters of galaxies. Here's the bigger cluster, here's the smaller cluster. As they pass through each other, the gas got stripped out, and in fact you can even see this gas here sort of in a little Bose-shock formation as a result of all the fluid interactions. You could do simple fluid modeling to show that, yeah, it really works like this. So you have here all the galaxies which just passed each other. They're like the handfuls of sand, and collected in the middle you have all the fluid, you have all of the intracluster gas stripped out and stuck in the middle. But then what blue is, the blue haze, is where is most of the mass of this cluster. Now most of the baryonic mass is here, because we know that most of the baryonic mass is in this X-ray emitting gas. So most of the baryonic mass is stuck in the middle. But most of the overall mass is out here with the galaxies, i.e. behaving like collisionless particles. So all the stuff we can see, 10% of it's out here, and then 90% of it's in here. But the mass affecting the background galaxies from weak lensing is out here. So what this is that most of the mass is not where most of the baryonic mass is. And so this tells us dark matter must exist. This is a really straight, direct detection of mass that is present, but is not where the mass we can see is not where the baryonic mass is, right? So I'd say even by the criterion of that review article from 2002, MOND is now more speculative than dark matter. Arr! All right. So we're seeing mass that's not where the baryonic mass is. There must be dark matter. Even if you think, this doesn't mean that MOND is wrong. It just means it's more speculative. But even if you modify Newton's dynamics, you still need dark matter in order to explain this observation. Even if you don't like the fact that my cosmology arguments were based on, hey, my cosmology theory explains so much, and I need dark matter to make it work, and you think that that's ad hoc, even then, you need dark matter to explain this observation. Dark matter really exists. All right, so Rudy and Moon just asked almost the same question. Dark matter does not interact with itself other than gravitationally. For the most part, that's true. It'll interact with itself probably via the weak force, but that's very infrequent. Right? So dark matter has mass, but is collisionless, and yes, and that's because basically it doesn't interact with itself, right? Except via gravity. Collision is what happens when you get strong interactions when two particles move close to each other. I don't know a lot about mirror matter, so I can't really say a whole lot. So it is going right through us, yes. There's not a lot of it. The density of dark matter is much less than the density of air, but it is still going through it. But it still has a particle nature. Yeah, so it's like neutrinos. Neutrinos do that. Here's my little comic, but I'll skip that because we're out of time. So here's my summary. Dark matter makes up most of the mass of galaxies and galaxy clusters. Something like 90% of the mass of galaxies and galaxy clusters is dark matter. It's spread diffusely throughout galaxies, but it's localized there. Right? It clumps in galaxies and it clumps in galaxy clusters. Okay? It cannot be made up of normal stuff, protons and neutrons. We have a few lines of argument for that. The early universe element formation tells us we don't have enough protons and neutrons. Also, we saw in the bullet cluster that it's got to be non-baryonic. It doesn't interact with light at all, only interacts weakly via gravity. Well, this is slightly wrong in that it actually interacts with light via gravity. Okay, fine. But it does not interact directly with light. It doesn't emit or absorb light. It only interacts with light via gravity. And that's how it interacts with everything else. And it has been detected multiple ways, and this is really the key thing here. Multiple different ways we've detected dark matter from the effect of its gravity. Right? Cosmology models, kinematics of galaxy clusters, structure formation and cosmology. Interacting clusters where we see the gravitational lensing shows us the dark matter is not where the baryonic matter is. Multiple different ways. We have detected the effect of its gravity. We have seen there has to be something there doing gravity that's not baryonic. And it's real. We cannot explain all of the observations anymore just by modifying our theory of gravity. And so that's the end, that's the summary. So yeah, so well, 85%, 90, 95%. Yeah, something like 85% of matter. Well, so here's the numbers. 5% of the energy density of the universe is normal matter, and 25% is dark matter, something like that. Right? So about 5/6, more or less, of the mass, of the regular mass is dark matter, as opposed to dark energy. Right, so the positron, yes, so that's still not confirmed. I'd say that's sort of speculative. Does dark matter exist between galaxies? Yes, although it is lower density there than it is inside a galaxy. So if you look at our galaxy and the Andromeda galaxy, the dark matter halos, so the Andromeda galaxy is about, 3 million light years away, something like that. And each galaxy is about 100,000 light years across. All right. So the ratio of the distance between them to their size is like 30-1. So it's like take 2 quarters and put them a meter apart. That's a little model of us in the Andromeda galaxies. Our dark matter halos extend out a factor of 10 times farther than the stars do, so their dark matter halos actually overlap. So yes, dark matter exists between galaxies, but it's concentrated in the galaxies and in the galaxy clusters. If you look at the big cosmic voids, there's a little bit of dark matter even there, but it's a whole lot less than there is in the clusters of galaxies. So it's clumped in galaxies, but it's much more diffuse than the stars and the gas. Right? So think of a big kind of halo, and when I say halo, don't think of a round ring, but think of what happens when you have a lot of salt water in your eyes and you look at a light and you see a big glow around it. That's a big halo. Think of that as the dark matter, and then the light bulb right at the center is the stars and the gas. That's kind of how galaxies are. All right, other questions? And I know I missed some questions early on, so feel free to ask them again right now. Yeah, so right. So dark matter and the density of dark matter in the room where you are is very low. We're in a very high density normal matter stuff. So it's extremely low, but yeah, there's dark matter occasionally going through you. Oh, good. And Bao found the dark matter wrap. Do we have any idea about the probable direction of velocity of the dark matter particles? Yes, every direction. So the dark matter halo as a whole is at rest with respect to our galaxy. So they're going in every which direction. The velocities we know have to be, I mean, the velocities are probably high because they're particles, but they have to be low so that the kinetic energy, and I'll go ahead and say 1/2 mv squared, where v is the velocity and m is the mass, their kinetic energy has to be a whole lot less than mc squared. That's what we call cold dark matter. Cold dark matter means dark matter whose average velocities are non-relativistic, right? To make all the cosmology models work and everything else, we need cold dark matter. So dark matter velocities, it'll depend on what their masses are, but their velocities are such that their kinetic energy is a whole lot less than their mass energy. Found a large clump of dark matter near Earth. I'm not sure about that. Dark matter does clump, it turns out, on sizes even smaller than galaxies. You can find some sub-halo concentrations of dark matter, but again, remember that the clumping is going to be on scales of at least hundreds and probably thousands of light years. It's not clumping on star or planet or solar system sizes. If neutrons are affected by magnetic fields, why can't they be contained in a magnetic vessel for nuclear fusion? Because they're not nearly as strongly affected as charged particles are, right? So they're affected by magnetic fields, but a proton is affected a whole lot more. Does dark matter exist in the center of the Earth or the center of the Sun? Yes, but it exists in the center of the Earth in basically the same concentration as it does at the surface of the Earth, right? A little bit more, but not much. So the gravity well of the Earth is not big enough to really collect dark matter. The same with the Sun, all right? So it's spread uniformly and permeates through all of it. So basically it's at the center of the Sun. Yeah, it's the same as what's going through Moon and everybody else too. Could the clumping account for the Kobe data anisotropy? Are you talking about the low order data anisotropy? I actually haven't kept up with that, and I'm not sure what current thinking is about the lowest order Kobe data anisotropy, and maybe a dark matter subhalo clump could do it. I'm not sure. Yes, so the dark matter clump, well, okay, that's saying it a little backwards, though. They're gravitationally bound to the galaxies, yes, but most of the mass of the galaxies is dark matter, right? So they're gravitationally bound to themselves. It's not really right to say that it's gravitationally bound to the galaxy if you're talking about all the stars in the galaxy. It's mostly dark matter. So it's mostly the dark matter that is keeping all the stars gravitationally bound to the galaxy. So yes, so the velocities have to be low enough to allow them to clump, but they have to be high enough that they don't clump even more. Right? So you can set some limits on that, and I can't actually tell you what those limits are because I don't know. But it's about the same as the stars. No, it's probably faster than the stars because it's spread out farther than the stars, right? The dark matter halos are spread out 10 times the size of the stars and the gas. So you're going to expect velocities that are higher than the velocities of the stars as a result of that. Any other questions? All right, here's a long question. Could there be some kind of intermediate stuff between regular matter and energy? Could the gravitational properties attributed to dark matter be an effect of the constant change between matter and energy, the interconversions that are going on all the time, not really stuff, but an effect? Why are we calling it matter when it seems so little like matter? Does dark matter seem to clump in any way that relates to matter to energy conversions? That's highly speculative. I'm not sure. I'm not even sure exactly what it would mean to say something intermediate between matter and energy. Matter is a form of energy, and when I say matter, what I mean is something with mass. And a particle either has mass or it doesn't. It can have a very low mass. So if you have, if you have a particle that has low mass and is moving fast enough that its radiation, that its velocity is, or its kinetic energy is much higher than its mass energy, right? So it's moving very close to the speed of light. It behaves more like radiation than like matter. So in fact, in the very early universe, very, very early universe, we can treat electrons as massless. Why? Because their kinetic energy is so much higher than their mass energy. So when I say matter, what I really mean is something that has mass, but even more than that, it means something that has mass that matters, right? Mass that's significant. So is there something intermediate between mass and radiation? I'm not really sure what that would mean. There's a black hole at the center of the galaxy, and the sun is not at the center. Does the sun move around the black hole, and does dark matter keep the sun locked in place so that it does not enter the black hole's event horizon? There is a black hole at the center of our galaxy, but the mass of it is tiny compared to the mass of our galaxy. So the overall mass of our galaxy is, are you ready for this, 10 to the 12 solar masses, which is 1,000,000 billion solar masses, I think. Something like that. Whereas the mass of the black hole is only a few million solar masses. So it's a supermassive black hole. It's huge, it's scary, but it's tiny compared to the galaxy as a whole. So when it comes to the dynamics of stuff like the sun far from the center of the black hole is irrelevant. All right? It's not the black hole's gravity is a whole lot less than the gravity of all the stars between us and the center of the galaxy, and it's a whole lot less than the mass of all the dark matter. So there is a supermassive black hole there, but this far from it, its gravity is just gravity, and it's very small compared to anything else. So there's no worry about the black hole at the center of our galaxy. There's no worry about falling in or not. It's just because we're moving fast enough that we stay in a circular orbit that is 20,000 light years from the center of the galaxy. That's what keeps us from falling into the center of the galaxy. So it's not dark matter per se, although we do need dark matter to explain our velocity, but without dark matter, we go winging off into intergalactic space. So in fact, the dark matter is holding us closer to that black hole. So we're not orbiting the black hole. We're not orbiting the black hole. We're orbiting the center of the galaxy. The black hole happens to be at the place that we're orbiting, but it's not the black hole's gravity that's holding us in. So the density is low within the Earth and the Sun because dark matter doesn't interact collide. So it blows right through the center of mass of the Earth and the Sun. It just keeps going rather than splats to a stop. Exactly. That's exactly right. Neutrinos do the same thing. There's this great Isaac Asimov quote that he said, "To a neutrino, matter is just a high grade of vacuum." Why is the black hole there? Well, that's actually a pretty hard question that that a lot of people are working hard on right now. But ultimately, it comes from the fact that it is the center gravity well of the galaxy. It's the place where most mass concentrates, and so enough mass concentrated there to form a black hole. Now, there's sort of we don't know. Do galaxies form first, or do black holes form first? Where do the first black holes come from? Where do the first stars come from? We have some ideas about that, and we're starting to get data on that. But that's an active field in astronomy research right now. Is the rate of dark matter infall into the black hole significantly greater than the rate of Hawking radiation, so that the black hole will not evaporate until it's captured nearly all the dark matter? Don't know. The problem is dark matter infall to the black hole rate is very small because most of the dark matter is spread out. It's going to take many times the age of the universe to significantly increase the mass of black holes by sucking up dark matter. Right? There's so much more dark matter than black holes that it will take a long time for the dark matter to move through the universe and capture all that, or make time for the black holes to move through the universe and capture all that dark matter. So honestly, I'm not sure how the timescale of that compares to the Hawking radiation timescale. So I'm not really sure. Doesn't dark matter sound an awful like the modern equivalent of the ether? And I'll say no. Where the ether came from. So what the ether is, in the late 19th century, we had physics was beautiful. We had great theories of everything, and in fact, many physicists felt like we were almost done, that we had almost explained everything. Well, some of the things we had were Newton's laws, which told us, and Newton's laws applied to all kinds of stuff, could explain wave motions, like the waves on the ocean you can explain with Newton's laws. You can use Newton's laws even to explain sound waves through the air. Yeah, not entirely, but mostly. It's great. We also had this great theory of electromagnetism. Now, there was a little problem, though, that said that electromagnetism gave us a certain particular speed that light moved at. And what is that speed relative to? Well, electromagnetism didn't really tell us. Newton's laws always say if you have a speed, it has to be relative to something. And light said, light's moving at this speed, and what is it relative to? So people, not knowing how to deal with this, invented the ether as the thing that light is waving. Okay? Now, and yes, you can draw an analogy and say, okay, you had some things where your observations and your theory didn't make sense, so you invented new stuff. You invented new stuff to explain and make all your observations work right. Okay, kind of the same thing as dark matter. The difference is ether was invented to explain a contradiction which we were able to resolve theoretically with relativity. What's more, there were direct experiments. The ether made predictions. Okay, if there's really an ether, then at different stages in the Earth's orbit, we ought to see different speeds of light going in one direction and the other direction because we're moving differently through the ether. Yeah, the Michelson-Morley experiment. The experiment was one and we didn't see it. Now with dark matter, there are predictions made. For example, if you have non-baryonic dark matter and two galaxy clusters collide, most of the dark matter should, and thus most of the mass, should just pass through each other and not collect in the center. Well, we did that experiment, and we saw the result. So dark matter, predictions have been made for dark matter that have been borne up. So dark matter, we have a lot of evidence for dark matter. It's not just an accounting problem. It's not just, I can't get everything to work out, so I'm going to add dark matter. At this point, we have a whole bunch of stuff that needs dark matter to be explained, right? It'd be like trying to explain why things fall to the Earth without using gravity, all right? Well, Aristotle did that. He didn't, his idea of gravity was that everything had a natural place, and heavier things' natural place was lower. But that doesn't explain about the stars orbiting the sun, and eventually we explained all that with gravity. Nowadays, dark matter explains so many different things that it's not just an ad hoc, we can't explain this. It explains many different things, and it has made predictions that have, yes, the spaghetti monster. Dark matter theories have made predictions that we've then later observed. So dark matter is very different from the ether, and that we know it's there. That's right. George says also independent lines of evidence, whereas the ether was based on one sort of conflict, one discrepancy. With dark matter, we've looked at it a whole bunch of different ways. Yes, intelligent falling theory. I recommend you search that on the web. It's an Onion article from about 6 or 8 years ago about intelligent falling. That really explains gravity. Any other questions? If not, I think I'm going to go ahead and have lunch because I'm kind of hungry. Do I want to show my cartoon? Sure. The cartoon was all about Mond. All right, thank you all for coming.